We are going to continue the oxidation process that we have discussed the last time. Okay. Well, let me just review briefly what you have discussed the last time. In a Deer and groove model, what we are saying is we have three fluxes. One is the diffusion of oxidant in air to the surface of the oxide, if this is the oxide and this is the silicon, and this is air. There's a flux F1 in the air to the surface of the silicon oxide, and there is a flux F2 which is related to the diffusion of the oxidant, and there is a flux F3 which is related to the surface reaction of the oxidation. So at the steady state, obviously F1 should be equal to the F2 should be equal to the F3. Okay, otherwise we have some accumulation or depletion of oxidant in this two interface. Okay, that's not going to happen at the steady state. So we have F1 is equal to F2 and F3. Okay, so we have driven the equation related to the oxide thickness, and we have found two constants. One is the B, and that is parabolic rate constant related to the oxide thickness, and that is the oxide thickness is going to be like BT squared, something like this, right? And it happens at the long time of oxidation. Okay, and we have another constant which is going to be B over A, and that is going to be called linear rate constant. And in this case, the X0, the oxide thickness, now is going to be linearly related to the time, and it happens at the short time of oxidation. So basically what we are saying here is that the oxide thickness at the first of the oxidation, somehow it is a straight line, and then that the straight line is related to the B over A, and at later we are going to square root of T, and then oxide thickness is going to be proportional to the square root of T, like this. Okay, we have somewhere in the middle. So that's the conclusion that we have discussed the last time. And today we are going to discuss some of the experimental results after this, okay? And that has been shown as figures in your note, and it starts with okay, here we go. This is the first figure, and what it says here is that here we have the parabolic rate constant, and this curve is the real, the full equation related to the oxide thickness, okay, x square and a x naught plus b, blah, blah, something like that, okay? That is the real plot, and you can see at the early stage of oxidation, we are going to have a straight line, and then the reaction constant is going to be b over a. That's a linear constant. And then at the later oxidation, we are going to have a parabolic rate constant, as you can see there. So this figure shows that the real curve for the oxidation at the beginning and at later we have a linear rate constant, and later we have a parabolic rate constant. That's what this figure says. Okay, and in this figure, at the early stage, the short time, we are going to have a b over a, okay, linear rate constant there. So the slope here is the linear is related to the linear rate constant, and that the linear rate constant is different along the crystallographic direction and the oxidation environment. One thing obvious is that when you have a dry oxidation and compared to the wet oxidation, you're going to have a low linear rate constant. In other words, you're going to have a slow oxidation in the early stage, at the early stage of oxidation, okay? But in any case, we're going to have a high oxidation rate on the crystallographic 100, I'm sorry, not the oxidation rate, but the linear rate constant, b over a, we have a higher value along the 100 crystallographic directions comparing to the that of 111 crystallographic directions. And that is because we have a different activation energies in the along the different crystallographic directions, okay? Because we have a different atomic density, right? We have seen that 100 and 111, this is a close packed density we have in the silicon, and the atomic density is much greater than here, and that the p over a constant is somehow is the Arrhenius type related thing. Now, surface reaction constant, for example, K is e to the minus E star over KT, okay? It's a thermally activated process. So it has a different activation energy for the 100, the same activation energy for the 100 and 111, but the absolute, because the slope is the same, okay? But it has a different activation energy with the environment. If it is a dry oxidation, we have a slope slower than that in the wet oxidation case, okay? So the activation energy is different this E star is different from the crystal environment, okay? So the activation energy for the H2O is greater than the activation energy of O2, okay? But the activation energy in 111 is same to the activation energy in 100. And the reason why for this is the oxidation is virtually related to the bonding energy of silicon. Okay? Actually, what it does is you break the bonding between the silicon-silicon bonding, and then you're going to have a new bonding with the oxygen. That's what the oxidation is for, right? So this activation energy should be related to the bonding energy of the silicon, so that no matter what the atomic density is, the activation energy should be the same. But depending on the environment, H2O or the O2, the activation energy, this bonding, breaking the bonding, is efficiency of the breaking bonding, I should say, is different depending on the environment. So that's what we can see in this figure. Okay, and the next figure is about the parabolic rate constant. Parabolic rate constant is constant B in that discussion that we have made. And you can see in the dry oxidation, you can see the activation energy is 1.23, and the activation energy for the parabolic rate constant is, in case of H2O, is about 0.78. It's much lower. So in this figure, we can arrange things something like this. Okay. From this figure, what you can see here is the parabolic rate constant can be expressed by the Arrhenius type plot, where E1 over KT, okay? And then you can see the dry oxidation case and wet oxidation case, and pyrogenic oxidation case. Three cases have been compared, and the C1 value is 10 to the second micron square per hour. If it has a unit, something like this, then it's 7.72, 2.14, and 3.86. You have a different value for the C1 here for the environment, and E1, the activation energy is electron volts, 1.23, 0.71, and 0.78. We all have different values here. And one thing we should notice here, as far as B is concerned, B111 should be equal to B110, should be equal to B100. That's what we can see in this figure. And that is, that should be pretty much so, because as far as D is concerned, B is nothing but the diffusion of oxidant, okay? Diffusion of oxidant. We don't know what the oxidant is really. It can be O two molecule, O2 minus or O2 minus minus, okay, oxygen minus, we don't know what that is going to be. It can be H2O something, you know. We don't know what exactly what that oxygen is, but something which is going to be used for the oxidation of the silicon surface, that is going to be called the oxidant. And the rate constant B is related to the diffusion of this oxidant, so that it doesn't care what the surface is going to look like, whether it is 111, 100, 10, it doesn't care. It doesn't really physically related to the constant B. Okay, so that's why we have in one straight line we have different values on the different. We have same values on different crystallographic directions. But this is what we can summarize in this figure. Okay? And then the next figure is linear rate constants. Linear rate constants is a silicon-silicon bonding related property. And in this figure, linear rate constant also can be expressed in an Arrhenius type plot, thermally activated process. So now we can see that the linear rate constant B over A, that is related to the silicon bonding energy, is nothing to do with the diffusion of the oxidant in this case. And from this figure, what we can see, again, here C2 and E2, now B over A is kind of a C2 e to the minus E2 over KT. If you can express this as this equation, and dry O2 and wet O2 and the pyro again, see 6.23 times 10 to the 6, 8.95 to the 10 to the 7, and 1.63 times 10 to the 8. Well, different values for the rate, the constant here, and the activation energy, dry oxidation, wet oxidation, it doesn't care. It's the same energy, 2 electron volts, and it's almost the same, 2.505. By the way, this 2 volts, 2 electron volts, is really the bonding energy of silicon bonding energies. Okay, so this fact, the activation energy is about 2 electron volt, reflects the fact that this oxidation process is really related to the silicon bonding. Okay, so it's a very natural, and in this case, B over A, differently from the B, now B over A is very much dependent on the crystallographic directions. B over A 1, 0, B over A 1, 0, 0. So if you have a plane more densely populated with the silicon, then the rate constant is bigger. Okay? Well, you can interpret this as if you have silicon available for the oxidation, more and more silicon is available for the oxidation, then you're going to have a more bigger number for the rate constant. That seems very likely so, okay? And the next figure is an interesting figure here. The oxide thickness and oxidation time. And you can see at the different temperatures, the oxidation rate along the crystallographic direction is very much different as you go down to the low temperature. This means at the low temperature, the surface reaction flux F3, which is related to the reaction at the interface between oxide and silicon, that is more important. And as you go high temperature, then the diffusion of the oxidant in the oxide thickness is more important, so that as we discussed in the former figures, at high temperature, the rate constant, the B is important, so that the B is not changing along the crystallographic directions, so that we have, at the high temperature, the oxidation rate along the different crystallographic direction is not that significant. But as you go down the temperature to the lower temperature, you can see there are much difference in the oxidation rate along the depending on the different crystallographic directions. And it's the same in case of wet oxidation. In wet oxidation case, you just see that the difference along the dependency, sensitivity, I should say, sensitivity to the temperature is not that great, but is you do see the fact that as you go down to the low temperature, you can see the gap between gap in the oxidation rate between the different crystallographic directions becomes larger and larger as you go down the temperature. One thing you should notice is that in the wet oxidation, in this plot, the Y scale is very much different from the dry oxidation case. Okay, the wet oxidation is much faster than the dry oxidation. Okay, and that the linear rate constant and probability rate constant in a different environment has been tabulated in this table, so that you can just take a reference at it. I skipped these two figures. Okay, so in Dewey and Grove model, the two constants, B over A and B, probability rate constant and linear rate constant, has been developed in his theory. And at the initial stage, the oxidation rate is linearly proportional to the time. But as the oxidation goes developed, you can see that the oxidation rate is parabolically dependent on the time. And that's what the life is. Okay, everything happens that way. Initially, you have a very fast growth rate in everything. And then as you have more and more thicker and thicker oxide, then it's slowed down. That's what, that seems very natural, isn't it? Okay, now we have a special topic has been shown in a note, which is the initial rapid oxidation in dry oxidation. Okay, this is the experimental results. That is the oxidation time here, and then it has been according to the Deal and Grove model, we have seen that wet oxidation is very much faster. Wet oxidation rate in the wet oxidation environment is much higher than that in the dry oxidation environment. But in this figure, at the very early stage, okay, from here to here, wet oxidation grows this fashion, but the dry oxidation goes this way. So that from here to here, you can see the dry oxidation rate is higher than the wet oxidation rate. That's very strange, isn't it? And then you extrapolate this dry oxidation, and you can see the incubation time, say incubation time tau there, by extrapolation, and then that corresponding to the 150 to 200 angstrom. But in a wet oxidation case, this incubation oxide thickness is corresponding to just 5 angstrom, which means in wet oxidation it doesn't have any incubation time for the oxidation, but in the dry oxidation it doesn't need the incubation time for the oxidation, things like that, okay? And the reason here, it is not clearly understood yet, but the postulate, one of the postulate speculations that we have done for this is that this oxidant may be ionized in this fashion, and then if we have space charge regions at the surface of a silicon, which is known as a Debye length, okay, and then that electric field is going to exist in that space charge region, and that electric field is going to enhance this oxidation rate if the oxidant is somehow has charges like this. And that is one of the speculation to explain why we have a fast, rapid oxidation rate in the dry oxidation at very early stage of the oxidation than that of wet oxidation. But this is very important to notice, because in modern devices, the gate oxide thickness is about 100 angstrom, that thin. So in industry, the oxidation happens just 100 angstrom or so. So if that oxide, dry oxidation is much faster than the wet oxide, then this effect, rapid oxidation in dry oxidation, this phenomenon is very important. You have to, you should notice this effect. Okay. Now this is the one of the figures that I've shown you earlier. That is the oxidation furnace, and you have a boat. We call this boat. You load the wafers vertically, and then you blow the oxygen, and you elevate the temperature, something like that, to 1,000 degrees centigrade or so, and then you get a certain thickness of oxide, on the silicon wafer, then you just take it out. And since this the number of silicon wafers excuse me, loading at one time is more than 100, or even it can reach 200 wafers at a time. Normally it cannot be loaded with the normal equipment. So we use a cantilever system for this. Okay, and oxidation time is about 30 minutes or so. Then the time necessary to load the 100 or 200 wafer has to be taken into account. Otherwise, you are going to have a different thickness of the oxide. Okay, so there is not a simple process at all in a mass production industries. Now, how do you evaluate the final thickness of the oxide if you have to carry out the multiple steps for the oxidation? For example, if you have done the oxidation at the 700 degrees centigrade in the wet oxidation, and then you do the 800 degrees centigrade in the dry oxidation, for example, for an hour, then what is going to be the final oxide thickness? And to answer that, what you have to do is you just come to the table or the figure, and firstly you done a 700 degrees centigrade of wet oxidation in 1 hour, then you end up with a time corresponding to the 800 degrees centigrade dry oxidation process. And that is going to be the T star. And this T star is going to be added to the final process of 800 degrees centigrade oxidation. So let me just write down what I'm talking about. Okay. Now, if you carried out the oxidation at 700 degrees centigrade in a wet oxidation environment for an hour, and followed by at 800 degrees centigrade in a dry oxidation for, let's say, 2 hours. What is final oxide thickness? This is the question. To answer that, what you have to do is you just go for the table for the curve, this oxide thickness, and then this is the time. And you follow the curve at the 700 degrees centigrade. Let's suppose you have a curve something like this: 700 degrees centigrade in the wet oxidation, and you have done for 1 hour, so you just pick up 1 hour, and then you have this oxide thickness corresponding with this. But what you have to do is, this is the final oxidation process that you have. You have this oxide thickness, okay, should be overlapped to the curve, which is in 800 degrees centigrade in a dry oxidation. So with this process, how much time you have to spend to get this thickness, and that is this point, and then you find out the time necessary for that thickness that you have got by this process in this process, and that is going to be the T star, okay? And then you just use that the T star and the 2 hour, you have done the 2 hours, so you are going to follow this time, and then you're going to have the thickness here. And this is the thickness of your oxide, the final. Can you see this? Okay? So whenever you do, you have to do this. Let me arrange this thing again. If you have a multiple step for the oxidation, then the previous oxide thickness should be converted to the time necessary to get that thickness at the final, under the final environment. And then that time should be added to the final, the time you carried out at the final environment. So that as if you have carried out the oxidation for 2 hours and T star here at this environment. Okay? And that's how you can get the final oxide thickness. You should not do this. You just calculate or find the oxide thickness corresponding to this, and then you just find the oxide thickness with this process, and then the final thickness is going to be x1 plus x2. This is wrong. Okay? Obviously, this cannot be true. One of the merit of this oxide is, since it is transparent, okay, we can check the thickness by its color, the optical color, because we have the destructive interference according to this equation, okay? The oxide is transparent. So what happens is that if you have a silicon here, okay, and then this is the silicon oxide, then you shine the light, and one is going to reflect from the bottom, and you're going to have another one reflected from the top. So the destructive interference, will show you the color, and then that the destructive interference happens at the odd multiple of the half wavelength, right? So if this half wavelength, the wavelength of the light, is corresponding to the odd number, 2k minus 1, divided by the refractive index in there. If that happens to the thickness here of the oxide, then you're going to have a destructive interference, and then they're going to give you the color optically. And you can see in this table, we have all different colors at the 50 angstrom differences, like tan, brown, dark violet to red violet, royal blue, light blue, things like that. That separation of the color is just corresponding to the 50 angstrom or so. So very sensitive, actually. But the problem is, how can you tell that is tan and brown? You cannot really distinguish tan and brown because it is the same type of the color, right? So in actual practice, we do not use just this reflective color to identify the thickness of the oxide. But this fact is very useful to find out whether the oxide formed on the silicon is uniform or not. If it is not uniform, okay, you can see the rainbow. You can see the color change. So that is very easy to see, to identify. So this reflective color, we just use that for checking the uniformity of the oxide formed on the silicon, not just to find out the absolute thickness, because the color change in between this 50 angstrom is not that obvious in the color. So let's suppose you have a single crystal silicon bowl, for example. If you put that silicon bowl in the furnace, what's going to happen? If you put that thing in the oxidation furnace and take out, then you'll see beautiful rainbow formed on the silicon bowl, single crystal bowl. Because as we discussed in earlier, this oxide thickness, depending on the crystallographic direction, is all different. Okay, so you have all different thickness of oxide on every surface of the bowl, so that if you have a silicon bowl of a single crystal, and then you put it in the furnace, and then after the oxidation you take it out, then you're going to have all beautiful reflective colors, rainbow colors in there. Okay. Any questions? On Wednesday, let's discuss about this on Wednesday. On Wednesday, we're going to discuss about the charges and the silicon oxide, and that is very important. Let me see, what time is it? Okay, let's discuss about the charges in the oxide the next week, and then advance the topic in oxidation, the dopant redistribution and masking properties of the oxide, and the dopant effect on the oxidation rate, and finally the HCl oxidation, which is very important in the industries. Okay, every oxidation is really happens in this HCl environment because it's so powerful in forming the oxide. Okay? So I'll see you on Wednesday then.